I've been looking a lot at algebra and numbers, all the letters of our mathematical alphabet. Functions. Let's now put them into sentences, if you like. So, a function. Some definitions to start off with. A relation. A relation is simply a rule that maps between two sets of values. So here we go, we've got a set that I've called X, a set that I've gone Y, and we can see arrows going in all sorts of directions. So -1 maps to -2 and things like that. That actually is the relation of what we know is a circle. X squared plus Y squared is equal to 5. That's the relation that exists between these two sets. Now a function is a very special type of relation, where it uniquely maps. You'll notice with our arrows on this set, you can see that each number, there's only one arrow coming from each number. That is the function of y equals x squared. Independent variable. It's the input, if you like, of the function, the number that you substitute into the function. That brings us up to this thing called domain, also known as the natural domain of a function, is all the possible values that the independent variable can take, the things that we can substitute in and get an answer. Now sometimes we have to restrict domains. So restricted ones are where some values are not required. We're only interested in some piece of the function. So an example here, if it was representing time, then we probably would only use t is greater than or equal to 0. We don't really talk about negative time. The dependent variable is then the output. So we put the number in, what gets spat out. Now, so its value depends on what you input, hence the name, dependent variable. So the range then is all the possible values, the dependent variable. So all the possible answers that it could take by substituting in every possible number from the domain. So we substitute every possible number in, what are all the possible numbers we get out. When you're drawing a graph of your function, you always put the independent variable on the horizontal axis. Hence why the horizontal axis is the x-axis, because traditionally we use x for the independent variable. I mean, it doesn't have to be x, there's no reason why it has to be, but traditionally we tend to use that and then y for the other one. Right. That brings us to function notation. So y equals, now more often than not we use f to say function, but again it doesn't have to be, you could use any letter you like. Probably not a good idea to use y or x because that might get confusing, but so the independent variable, that's what we're substituting in, it goes inside the function. So that's why we place it in there. And so f is representing whatever function we're substituting into, then y is the answer, the dependent variable. They're all the pieces of the function notation. So a very simple example, if our function is 3x squared plus 4, then function 5, they're saying, well, what do you get when you substitute 5? We get 79. Of course, you don't have to substitute a number in, you could substitute in another pronumeral. So function a would just be 3a squared plus 4. In fact, you could substitute in several pronumerals. So what would be function x plus h minus function x, substitute in x plus h, so 3 outside x plus h squared plus 4, minus just the function itself. And we end up with this lovely expression, 3x squared plus 6xh plus 3h squared, plus 4 minus 4, that'll cancel, the minus 3x squared will cancel as well. We've got 6xh plus 3h squared. Testing for functions. How do we know whether a particular relation is indeed a function? And the vertical line test, visually it's a lot easier to tell. You know, if you draw a straight line parallel to the y-axis, it'll only cross a function once, if at all, because you've got a maximum of one y value for any input. Example, our hyperbola, it does not matter where I draw a vertical line, it will only cut it once. And at 0, of course, it doesn't cut it at all. So that one's good, that is a function. As opposed to, say, a parabola on its side, sure, at x equals 0 we're okay, it'll only cut it once, but I can draw a vertical line in and cut it twice. So that one's no good. For an x value there, we get two possible y values. In fact, this relation is made up of two different functions. y equals the positive square root of x, which is the top half, and y equals minus the square root of x, which is the bottom half. They would be the functions associated here. Domain and range then. Let's talk a bit about that. How do we find a function's domain? Again, if you've got the picture, life becomes very easy because you can simply look at it. There's the parabola on its side, x equals y squared. I just look at it and go, well, where am I getting y values? You can even imagine walking along the x-axis and looking above you and looking below you. Do you see anything? And it's not until we get to 0 that we see something. Oh, hang on, here's our function. And we keep walking and yep, there's something above, something below. So our domain, I've written it as x is greater than or equal to 0. That would be the domain of this particular, well, it's not a function, domain of this relation. You got these sort of weird split graphs, and so again, where does it exist? Well, it exists at x is less than or equal to 0, and also x is greater than 2, not equal to, because we haven't coloured the circle in. If we don't know what the picture looks like, what do we look for algebraically? Key things we know. Fractions, if there's a fraction involved in it, well, we know that the bottom of the fraction can't equal 0. Maybe that's going to cause me some problems. Let's start with the very basic hyperbola, 1 on x. Well, hang on, I know the bottom of the fraction can't equal 0. But you do not write your domain like that, because the domain is about what's included, not what's excluded. So our domain I would write down something like this. Well, look, it's all real x, except x equals 0. I can't have that. There are different ways of writing it. Some people would say all real x except x can't equal 0. I guess it all just comes down to the grammar of how you're saying it. But as long as you make the point that 0 is this key point here, where it's not in the domain. So 1 on x squared minus 1, again, what's causing me the problem? It's the bottom of the fraction causing me the problem. That can't equal 0. So for this one, x can't equal plus or minus 1. So the domain is, well, I got everything. I got all real x. Except I can't have x equals plus or minus 1. Two fractions, well, the rules are still the same for both fractions. X minus 1 can't equal 0, so x can't equal 1. 7 minus x can't equal 0, so x also can't equal 7. So there's my domain. Everything except 1 and 7. Square root signs, that can cause problems as well. Right? You can't find the square root of a negative number. So therefore, whatever is under the square root sign has to be greater than or equal to 0. So I know 4 minus x squared is greater than or equal to 0. Solving that particular one, we end up with x is in between minus 2 and 2. There's our domain. And I can write that one that way because that is an inclusion. We're saying these are what are included. I've got two different square root signs, but the rule's the same for both. I know that x plus 3 can't equal 0, so x is greater than or equal to minus 3. But also 5 minus x has to be greater than or equal to 0. X is less than 5. Both of these things have to be true. Therefore, I must be in between minus 3 and 5. There's my domain. 1 on the square root of x plus 2, I've got both problems. Now I've got the bottom of the fraction and I've got a square root sign. Now the bottom of the fraction we'd say, well, can't equal 0. The square root sign we'd say x plus 2 is greater than or equal to 0. But it can't equal 0, we just said. So for this one it's just x plus 2 is greater than 0. Greater than negative 2 is what it ends up being. Okay, what about the range then? Okay, if I can see the picture, let's go back to our sideways parabola. Now we're climbing up the y-axis this time and looking to the side. Is there a curve there? And it doesn't matter where I am on the y-axis, there'll always be something there. So this one's simply everything. All real y. Everything's there. By the way, when you're writing it, make sure you do say the range is all real y, not all real numbers, anything like that. Because when we're looking at your solution, we need to know that you're understanding that the domain is referring to the x values and the range is referring to the y values. If you just put all reals, we don't know if you actually think the domain's the y values. So you need to let us know that. Our split function, so y would be less than or equal to 1 and y is greater than 3. But I don't know what the picture looks like. So what do I look for in the algebra? Things like this, maximum and minimum values, because the range is talking about the y value. So how high up does it go? How far down does it go? Is there anything there that would make it stop? Things like even powers and absolute values, they're always going to give me positive numbers. They're never going to be negative, the answer. Let's do the basic parabola, y equals x squared then. Well, I know then the range must be y is greater than or equal to 0, because that x squared will never be negative. It can only give me these sorts of answers. So logically, if I add 3 to it, then the smallest that could be would be 0 plus 3. Because the x squared part, the smallest it will be 0. So there's my range, y is greater than or equal to 3. 5 minus x squared, this time we've turned the x squared upside down. So even though I'm looking at the algebra in my head, I'm still thinking visually. Because I do know x squared is a parabola, but I'm turning that upside down. So I must have a maximum point rather than a minimum point. So y is less than or equal to 5 minus 0, y is less than or equal to 5. Absolute value, same sort of idea. Well, that one, absolute value's got to be greater than or equal to 0. Again, here's the absolute value, but I've now got minus 5 as well. So y has to be greater than or equal to minus 5. Are there restrictions on the domain? You see, if you've restricted the domain, then probably the range is going to be restricted as well, because you're only going to get a piece of the relation. Rule of thumb, good old rule of thumb, people. So, substitute in those endpoints, let's see what those y values are. You'll be amazed how many of these functions and relations we look at that have some sort of symmetry about it. So I'll also substitute in the centre as well. See what, and that's probably going to give me a good feel for what the range is. Y equals the square root of 4 minus x squared. We had a restricted domain for that one. X was in between minus 2 and 2. So when x equals 2, y is 0. I don't know that I worry about negative 2 because I'm squaring. It's going to give me the same answer. But in the centre, we've got 0. Sub in, we get 2. So yeah, a pretty fair bet this goes in between 0 and 2. And if you do recognise that shape, you'll know, yes, it does. That's our semicircle. Fractions. What happens with fractions? Well, if I've got a constant on the top of the fraction, then that fraction can never equal 0. I can't divide a constant number by something and get an answer of 0. Can't be done. Our basic hyperbola then. I've got 1 on the top of the fraction. So I know that fraction, which is y in this case, can't equal 0. So range will be everything except that y equals 0. 5 plus that, similar deal, the fraction can't equal 0, so therefore the whole thing can't equal 5. There's my range, everything except y equals 5. Ooh, x plus 7 on x plus 4, bit harder to tell. There are different ways we will see to handling this. At this stage, probably just do a polynomial division, I guess is what I'm saying. If I was to divide x plus 4 into x plus 7, I'd get 1 plus 3 on x plus 4. Well, now I've got a fraction where there's a constant in the top. I know that fraction can't equal 0. The y can't equal 1 plus 0. Everything except 1. Okay, so 3a and 3b.